In this video, we'll learn how to sketch the graph of an antiderivative given the graph of some function. So here's some function, f of x, here's its graph, it just turns out to be a line in this case. And what I want to try to do is I want to sketch a graph of y equals big F of x, an antiderivative of f of x. So this antiderivative will have f as its derivative. So when I think about big F of x and what is going to be happening, say, at x equals 0, I know that its derivative should have a value, whatever this value here is. Maybe we can put a number on this, let's call this like 1. So that means at 0, wherever I'm at 0, I should have slope that's 1. When I go past 0 further to the right, my slope should be getting bigger. It's more and more positive, 2, 3, so forth. So as I move to the right, my slope should be getting more and more steep. So as I move to the right, my slope should be getting steeper and steeper. To the left, well, here at 0, at x equals -1, so let's just call this like -1, say, my slope here would be the value of this function, because that's the derivative of big F. So my slope here should be 0, because that's the y value. F of x, which is the derivative of big F of x, is telling me what the slope is. So my slope should be 0. And as I move further to the left, now it should actually start having a negative slope. A negative slope. And further to the left still, an even more negative slope. So the slope should be getting steeper and steeper negative. So now I want to draw some graph that has these characteristics. So here's one. I could draw a graph that looks something like, here we go, something like this. Notice right here, my slope is 0. Right here, my slope is 0. And as I move to the right, my slope gets more and more and more positive. This guy's getting more and more and more positive. And as I move to the left, my slope's getting more and more negative, just as he's getting more and more negative. So there is some graph of an antiderivative. Now, I drew this particular one so that the antiderivative passed through, it satisfied f of 0 equals 0. But I could draw several other antiderivatives that have the same derivative f. I could instead have drawn the graph of, so if this is my f of x, I could instead draw the graph of something like y equals f of x plus a constant, say y equals f of x plus 3, and it would be the same graph, just shifted up some. So, okay, I guess this is probably shifted up less than 3. I don't know, maybe let's shift it up like 1.2 or something. Whatever it is, I've just shifted this graph up some, but it has the same slope. It has the same slope. So there's several different graphs for the antiderivative I could draw. These are all antiderivatives. I can put whatever constant I want here. The point is this can be any constant I want. And so I have several graphs here, just shifting it up or shifting it down by whatever constant I want. You should think there's infinitely many possible graphs that have y equals little f of x as its derivative. But if you then specify a point, and I say, well, I want to insist I'm talking about the graph that passes through the point 0, 0, then you pin down 1. In order to get a better idea of what's going on here, I want us to think about what's going on graphically. Not just graphically, but what's going on algebraically. So let me actually give this guy an equation. So my f of x here is just a line. If it's passing through the points -1 here at 1 here, that looks like the line x plus 1. So that looks like it's something like the line x plus 1. So when I go and I calculate my antiderivative, using the power rule in reverse, this becomes x squared, but then I need a 1/2 out front, and then I have a plus x. Then plus a constant. Whatever that constant term is, we can just say plus c, but remember it's just plus some constant. That plus a constant is why you have these infinitely many possibilities. Now, if I want to say, let me pin down the one that passes through, say, the origin, what I'm doing is I'm just introducing the condition that f of 0 equals 0. So then I'm just solving, well, if I plug in 0 to this guy, I get 0 plus my constant. I want to equal 0, so I get that my constant is 0. So it turns out that this green guy right here came out to just to be the graph f of x equals 1/2 x squared plus x, where my constant came out to equal 0. So my constant equals 0, so I don't need to put a constant at the end. Okay, so that gives me a particular antiderivative that passes through a given point. If I had changed that given point to be some other given point, maybe I want to pass through this point instead, I would have a different solution. Okay, now let's try another example, slightly more complicated, but same idea. I'm given some graph of y equals little f of x. I want to sketch a graph of an antiderivative, y equals big F of x, where I'm given that I want that antiderivative pass through the point 0, 1. When x is 0, I want this to pass through the point here, 1. Remember, there's going to be infinitely many possible antiderivatives, so this is pinning down which antiderivative graph I'm going to be drawing. To do that, we look at the graph of little f of x, because little f of x is the derivative of big F of x. Little f of x is the derivative of big F of x. And so I begin and I just say, okay, well down here I'm negative, so that means at this portion of the graph I should be going down with a slope of -1. But then as I move to the right, my slope is going to become less and less, so no longer -1, but a little bit less than -1, until I get to this value, where my slope becomes 0, so I become flat, and then I start having positive slope again, more and more positive as I move to the right. So a graph that looked something kind of like this would be something in the right ballpark. I don't know exactly how far down or up it goes, but something like this keeps going up and up and up. As I now move in the opposite direction, here my slope is still negative, but a little bit less negative, so it won't be slope -1, but a little bit less negative. Over here, when I get to this point, my slope is 0, so my slope is 0. And as I come back, a little bit positive slope. So right here, right there, my slope is 0. So right over this point, my slope is 0. But as I go back, I have a little bit of a positive slope. And as I go further back, further to the left, this becomes more and more positive slope. So more and more positive slope. So this should look something kind of like this. Okay, so it's just a sketch. It's just a crude sketch. But you get something like this. I've drawn the graph of y equals f of x. That satisfies that at 0 it passes through the point 1. We can always check this algebraically. To do that, I'm going to need an explicit formula for this guy. So let's say f of x, it looks like a parabola. This looks like it's just something like x squared, except here it passed through the point -1. When x was 0, the y value is -1. So this is probably something like the graph of x squared minus 1. Let's go ahead and calculate an antiderivative for this. So if I find big F of x using my power rule, I get that x squared becomes 1/3 x cubed, because I increase the 2 by 1, and then I put 1 over that power up front, minus the antiderivative of 1 is x, because the derivative of x is 1, plus now a constant. So I can just plus c, plus some constant. And I don't know what that constant is, except here's where I'm going to use this condition. I want that when I plug in 0, this should come out to be 1. So let's go ahead and check. When I plug in 0, I would have just 0 minus 0 plus my constant. So I just get that my constant is 1. My constant is 1. So this should correspond to the graph of f of x, big F of x, the antiderivative, is 1/3 x cubed minus x plus 1. If instead of plus 1, I had a plus 2 or a plus 3, I would just be getting the corresponding graph shifted up. No longer pass through the point 0, 1, it passed through a different point. So there are infinitely many graphs of the various antiderivatives that just correspond to the different constants below as well. You have infinitely many values for these antiderivative graphs. It's just this condition is pinning down one of them.